Hi, I'm Naveed, a PhD student from Aberdeen in Scotland. I'm going to present some of my research estimating detection heterogeneity without covariates in occupancy models. Let me introduce some challenges and how occupancy models can help. For species conservation, we need accurate estimates of population sizes to detect trends and ensure conservation management is effective. But during a survey, we don't find everything, so the probability of detecting our target organism needs estimating. A potential solution uses occupancy models, which estimate the detection probability by using data from multiple surveys. But there's a spatial heterogeneity problem, which occurs when the target is easier to find at some locations than others, and violates the basic assumption that the detection probability is constant across all sampling units. This heterogeneity leads to underestimates in the occupancy. Underestimates occur because models don't properly account for places with very low detection probabilities. So some places where the target is present but never found are included with those that are truly unoccupied. There's a further complication if a surveyor remembers previous survey results, as occupancy models also assume that detections are independent from those of earlier surveys. The memory of previous surveys may confound the heterogeneity if those easier to find are also more likely to be remembered. If covariates are available, these assumptions can be relaxed, but what if the covariates cannot be adequately measured? First, let's look at modelling the heterogeneity when detections are independent of previous surveys. Imagine doing a survey in the habitat pictured for something like lichens on trees. It may be much easier to find them in some locations than others, so the heterogeneity and detection probabilities would be high. But suitable covariates may be hard to obtain. We may need to measure shading, contrast with their substrate, numbers in a sampling unit and their spatial arrangement, and height and size on a tree. To model the heterogeneity without covariates, a Bayesian occupancy model is needed. The presence or absence at a site, Zi, is modelled as a Bernoulli random variable, for which we need a prior distribution where we expect the probability of a site being occupied, psi, comes from a beta distribution with an equal chance of any occupancy between 0 and 1. The detections H are also modelled as a Bernoulli variable, and the detection probability P is modelled as a logistic regression with a random effect for site, beta I, and a fixed effect for survey, beta J. Logic normal distributions are used to obtain the parameters for the regression equation, and of particular note is the standard deviation, sigma I highlighted, which determines the heterogeneity in detection probabilities for the site random effect. So, can we model the heterogeneity effectively? What parameter value is needed for its standard deviation? I set up my field experiment in this pine plantation, where the trees are similar, which helped us control the detection probability by using artificial lichens and varying their height, size, and numbers per tree. We made 3 types: a grey one from putty and soot, a sandy one from mastic, and a brown shrubby one from seaweed. And 16 surveyors searched 180 trees and recorded which lichens they found. We should note here that for lichens grown on trees, for each species, an occupied tree is counted as one lichen. So our sample unit and unit of occupancy is a tree, which corresponds to one individual. By using an artificial population, we know the true occupancy, so we can calculate the true or realized detection probabilities. Here's a plot of the true detection probabilities at each tree. On the x-axis is the probability, the red bars are the frequency, and the grey shaded area is the density plot for the detection probabilities. Although the distribution appears to have a tail, and the quantile plot shows deviation from normality at the extremes, it's assumed to be normally distributed. Is it possible to model these probabilities and thus heterogeneity effectively? In our regression equation for the detection probabilities, what parameter values should be used? In particular, what's the standard deviation for the heterogeneity distribution? The standard deviation is important since it helps the model determine how many trees were actually truly occupied but where no lichen was found. And what's an effective number of surveys? 7 different models were used for the standard deviation, with gamma, half normal, and half t prior distributions. Here's the results with 3 representative models for 2 surveys. On the x-axis is the standard deviation value, and on the y-axis is the density of the estimate. Note where the peak lies and its spread, the 95% intervals shown by the markers on the x-axis. The results for the gamma model, with a shape of 0.01 and a rate of 0.01 at the top, shows the highest concentration of estimates near zero, but the gamma with a shape of 1 and rate of 0.5, and half t with 1 degree of freedom and standard deviation of 2 allow larger estimates and peaks closer to 4. When we show the known standard deviation, which we can calculate separately because we know which lichens were found, we can see the estimates are a wee bit out. When we overlay the prior distributions, shaded in green, in the gamma model at the top, this is similar to the posterior and strongly informs the estimate, thus preventing us from independently modelling the heterogeneity from our survey data. The other gamma model and half T are better, as they have fatter tails and allow higher estimates. What about the occupancy estimate? Here the occupancy value is on the x-axis and the density of the estimate on the y-axis again. We see using 2 surveys gives us a wide range in possible occupancies, as shown by the highest density intervals. And although it covers the true occupancy, the model is estimating that somewhere between approximately half and all the trees are occupied, which is not very useful. For 3 surveys, the standard deviation estimate is closer to our expected value, just below 1, but the gamma distribution at the top still constrains the estimates close to 0. However, now we see models effectively estimate the occupancy and provide estimates within a reasonable interval compared to the true value. How about the occupancy estimate for other numbers of surveys? Here on the x-axis is the number of surveys, the y-axis the estimate mode, and the dotted horizontal line the true occupancy. Results are shown for 3 replicates for the half T with 1 degree of freedom and standard deviation of 2. We can see it's not very accurate with 2 surveys, and depending on which combination of 2 surveys are used, the estimates vary considerably. For 3, 4 and 8 surveys, the spread is narrower, with little improvement in using 8 rather than 3. And for 16 surveys, the estimate is very accurate. What about the estimate precision? For this, we can look at the 95% highest density interval. The numbers of surveys is on the x-axis, and the highest density interval on the y-axis. Again, 3 replicates are shown. For 2 surveys, we have a very wide interval, but which decreases for 3 and 4 surveys. And this time for 8 and 16 surveys, it is very narrow, with a big step in improvement between 4 and 8 surveys. So we need at least 3 surveys to model the heterogeneity. And the best prior for the heterogeneity standard deviation was the half T with 1 degree of freedom and standard deviation of 2, as this affected the posterior estimate the least. But care is needed as other priors may be too informative. Relying on lots of different surveyors may not be convenient or cost effective. So, could the same surveyor repeat some surveys? Remembering previous survey results would then be an issue, like remembering where this rare but distinctive lichen was. Occupancy models assume detections are independent from results of earlier surveys. But if detections were remembered, can we model the memory, or just use an effect for previous detections? The detection probability P was separated into 2 components, a discovery probability D of finding the target without any memory of previous detections, and a memory probability M that a surveyor remembers the lichen from the previous survey. An equation for memory was used in a similar model to those described earlier. To simplify the process, we assumed memory occurs first, that memory and discovery operate independently, memory depends only on the survey immediately previous, and discovery is not affected by whether it was detected on the previous survey or not. So the probability of detection, P, at site I on survey J equals the probability it was remembered, given it was detected on the previous survey, or the probability it was not remembered but rediscovered, given it was previously detected, or the probability it was discovered, given it was not previously detected. Models run on simulated data with and without memory and heterogeneity. This table summarizes the accuracy of the occupancy estimates for the different models on the different data. Along the top is the model used, and on the left the simulated dataset. Values are the difference between the true occupancy and the model estimate. In the first column, the occupancy is always underestimated for a simple model that doesn't model the heterogeneity or memory, especially if there is both memory and heterogeneity in the survey data. The star by the estimate means the true value was out with the highest density interval. In the second column, the model using an effect for previous detections does okay. It seems to overestimate if there's memory only in the data and underestimate if there is heterogeneity. But it performs generally better than the model that accounts for heterogeneity and memory in the third column. In the column on the right, we can see that using a model with memory and informed standard deviation for the heterogeneity performs very well when there's both memory and heterogeneity in the survey data. Not shown here is when any of these models are run with many surveys, for example 20, the occupancy estimates are all very accurate, regardless of model or simulated data. So, memory combines with heterogeneity to increase the occupancy underestimate, but we get very good occupancy estimates with a memory and heterogeneity model with informed heterogeneity, and using an effect for previous detections is okay too. To summarize, to improve the accuracy of occupancy model estimates, when there's detection heterogeneity only in the survey data, we need at least 3 surveys to identify it, taking care with which prior is used. But for survey data with heterogeneity and memory of previous detections, heterogeneity is not identifiable. So, many surveys are needed, or if using just a few surveys, we'd need to know the heterogeneity separately, which may require multiple surveyors or other methods such as time to detection. Finally, thank you to the volunteers and you for listening.